And let's move to the next talk that I have a pleasure to introduce. If we can switch the video. I'm really happy to introduce Andrew Davison from Imperial College London. So Andrew is a professor of robot vision and also head of the Dyson Robotics Lab at Imperial College. You may know Andrew well for his work on SLAM, on event camera, and various applications in robotics. So I could spend a long time to cite his really great contributions, but let me just hand to Andy and let him speak about his work.
Thank you very much, Kristen, and thanks to all the organizers. So can you hear me okay, just to check?
I believe yes, and YouTube will hear you in 10 seconds, I guess.
Good. Okay, let me just share my screen.
Yes, Andy, we can hear you.
Good. Okay, and can you see my screen share?
Yes, everything is fine.
Good. Okay, well let me start then. So yeah, it's a pleasure to take part in this workshop. So I'm going to speak to you about SLAM, a little bit of a kind of broad view of where I think we are in this field right now, and how I think it's evolving into something even bigger and more important that I call spatial AI. So we're at this pretty interesting point now in the history of SLAM, I think, especially for those of us who've been working in this field for a long time. And for me, it's really about 25 years now that I've been working on this since my PhD in Oxford. But we actually have products and systems out there on the market now that are enabled with visual SLAM. So these are in actually several different categories, and that's what's particularly interesting. It's not just about one type of product. Some of these are certainly what you would recognize as robots. So in the top left here, you can see robot vacuum cleaners. So this is the Dyson 360i, which was a product I was directly involved in working on with Dyson. We have smart drones from companies like DJI or Skydio with pretty advanced visual SLAM capabilities. We have visual SLAM in smartphones. There are capabilities like ARKit or AR Core from Apple and Google, pretty nice performance. And then there's this huge area of AR, VR headsets that need to be tracked in the world in order to enable smart augmentation, smart interaction. In many ways, these products are quite different. They have different combinations of sensors, but they've all kind of centered on cameras as really a core element of the sensing platform. Cameras have very nice points. They're cheap, they're small, and the potential upside of cameras in terms of what you can do with them is kind of almost limitless, I think. But if we look at what visual SLAM actually enables in products like this at the moment, it's largely about positioning and some level of mapping, which might be sparse or semi-dense. So all of these products can locate themselves accurately in the world relative to a map of landmarks. And then we have capabilities that are gradually coming in along the lines of dense and semantic mapping. So beyond positioning, smart devices need to understand, the shape of the world around them, and also increasingly, the content and identity of objects around them. And those capabilities are also, rapidly starting to enter products like this. So one way to think of this is a kind of a ladder or a set of levels. So this is an image from our startup SLAM Core, where we think of layers of performance in SLAM. from localization, which is where am I, to mapping, which is what's the shape of the world around me, to semantic understanding, which means, what are the things in that space around me. And I think what's really interesting is within this field of SLAM, we've gradually been building up through these levels, but generally while keeping in mind the kind of requirements of real-time interactive systems that hopefully you can actually get out and demo and test and put into real products. So I think the character of SLAM research that I've always enjoyed is it's been about actual demos, systems, open source code. It's not necessarily just performance on benchmarks and running on images and data sets. But then we've evolved, towards these gradually increasing capabilities. So I would say SLAM is evolving into something bigger, and I'm using this term spatial AI. And let's call spatial AI the online problem where vision is to be used, usually alongside other sensors, as part of the artificial intelligence which permits an embedded device to interact usefully with its environment. So here we're being clear that just localization and building a map is not the end point. It's not the aim in robotics or in other applications. The application is, the end point is intelligent operation of a device. So we're really turning attention to that now, and so that's very interesting. So where might that take us in a few years' time? Let's think about some potential breakthrough spatial AI equipped products of the future. So first of all, in robotics, and I should say very clearly, this is just a mock-up image I found on the internet somewhere, and certainly not representative of any product concepts at Davison or anywhere else. But let's imagine, what a robot of the future might be like. So an indoor robot. It might let's imagine a mass market, general purpose household robot for cleaning, tidying of complicated rooms and objects. It has a spatial AI system which is constrained by price, aesthetics, size, safety, and power usage, which must fit within the range of a consumer product. So this would be a very capable device that you could just say, clean my room and go out and come back and expect it to be done. So this is going to need a full sort of 3D spatial semantic understanding of the space. It's going to need to understand objects. It's probably going to need to understand physics. It's going to actually have to interact physically with objects. So that's, I think, pretty much far beyond anything we can do right now. And especially when we consider the constraints that a real product would have to fit within. So price, safety, power usage, all of those things. So another type of product, which I also think is pretty difficult to build, is the sort of augmented reality system which I think will eventually change the world. And of course there are companies working on this, but I think they've all realized just how hard it is. And I've called this a spatial AI product to stand for intelligence augmentation, which is a bit of a cute flipping of AI, but I think of it as AI with a human strongly in the loop. So the specs of this set of glasses might be along these lines: an augmented reality system with the form factor of a standard pair of glasses. So it's not going to be a chunky thing that sits on your head. I think if everyone's going to wear it all day, it's really got to look quite a lot like a normal pair of eyeglasses. But it would provide a robust and accurate real-time overlay and spatial memory of all places, objects, and people that you've come across. But here's the really tough thing: it should weigh 65 grams and have all-day battery life. So to make that point, more strongly, I think that these are products which will be hugely important when they arise. They don't exist yet, not because there's no demand, I think there is, but because no one yet knows how to build them. And that of course involves many different types of technology, both in robotics or eyewear. There's all sorts of problems to solve, but just within the sort of spatial AI area, I think we've got what current products can do. So these are the things I showed you in the first slide. We've got some things out there in research prototypes, in research labs, in companies, in universities. They're making some progress. But then I think there's still this big gap to cross to the capabilities that we need in these products that will really change the world. And I think the particular areas where we're lacking are robustness and efficiency. So robustness means devices that will really work in all sorts of different conditions, whatever you throw at them, they'll do something fairly sensible. And then this other key one is efficiency, and I'm particularly focused there on the power that algorithms and sensors and computation uses to actually come to actual inferences that are useful. So these devices may be connected to the cloud. Some computation may happen there, but they're going to have to do a lot of the computation actually on board, and they're not going to be able to carry around huge supercomputers. So efficiency is really important. So I've thought quite generally about this area of spatial AI, and in particular, this concept of the computational structure of spatial AI systems. So I've written a paper that you may find interesting. So this is a long discussion paper called Future Mapping, the Computational Structure of Spatial AI Systems. It's available from Archive, and it really studies this whole concept of what a spatial AI system could do and what are the prospects in particular for making that robust and efficient. So there's a few kind of hypotheses in that paper. One is this one. So to enable embodied AI, a spatial AI system should build a persistent and understandable scene representation, which is close to metric 3D geometry, at least locally. So what I mean by that is, let's imagine something like a robot whose job is to tidy up a room. So whereas there's certainly been work that's shown that devices can navigate without necessarily building maps. You don't necessarily need a metric map of a space to, for instance, walk from your house to the railway station. But if you really wanted to do something like tidy a room up, which might mean vacuuming every corner of the room, knowing when you've done everything, and remembering which parts you've done, which parts you haven't done, finding any object in the room and then knowing where to put it and actually traversing to put that object in the right place, then come back to where you were before, find other objects. It's very, very hard for me to imagine how you could carry out tasks like that without a concept of a map that you carry around. And that map may or may not be metrically precise 100%, but I think it's going to be somewhat close, at least locally and at least a lot of the time. So that's what I mean by that hypothesis. And another hypothesis is that there's a generality to spatial AI systems which will be useful for many applications with a fairly small number of performance measures or constraints, defining the differences between different systems. So what I mean by that is, I think that, we could think of quite different applications, a robot vacuum cleaner, a drone, eyewear. Clearly, they're going to have different performance parameters that are important in terms of accuracy, robustness in certain types of measure, semantic capability. But I think there may be a relatively small number of parameters, which you could think of as sliders that sort of set the performance of that system. But then under the hood, there's a relatively common spatial AI kind of workhorse that will apply to any of those problems. So those are kind of hypotheses. But I think that by working in this area of embodied intelligence, spatial AI, we may learn a lot about AI in general. We may learn a lot about, in general, embodied intelligence. What are the computations and storage patterns of the kind of memories of these systems that make such things possible? Okay, so let's move on and talk a little more concretely. So just a very sort of brief bit of history here and relating to these layers that I showed you earlier. So through my own research over the years, we've worked on sort of those different levels and really seen that cumulative build up in terms of capability. So I'd worked already on Visual SLAM for several years before this, but in 2003, a big kind of personal breakthrough for me was when I managed to make monocular SLAM work. So this was the MonoSLAM algorithm where we had the input of a single handheld camera moving around within a space, detecting and tracking landmark features in the scene, and then building a 3D map, jointly estimating the positions of those landmarks and the motion of the camera, and then showing that could all be done in a closed loop at 30 frames per second, on a 2003 laptop. And this was quite a breakthrough, and we showed that you could do some different things with that. We showed some augmented reality, we showed some humanoid robotics, for instance. The tracking was not super accurate at that time, mainly due to the relatively low number of features that we used. It was reasonably robust, but you had to move the camera kind of slowly and carefully. There was no additional inertial sensing that helped at that point, for instance. And then the real-time performance was enabled by quite kind of clever thinking about active processing. So we really paid attention to which parts of the image were most useful in giving accurate information about the camera position. So we worked on that for several years, and then the next kind of big milestone, I think, that was really important was around the time of about 2009 onwards. And this was particularly via the work of Richard Newcomb, who was working as a PhD student in my group at the time. And we started to show that we could do real-time dense or direct visual SLAM. So those are slightly different terms, dense and direct. Direct, as Daniel described earlier, refers to going straight back to raw pixel intensity information in terms of defining your cost functions. Dense means trying to use all of the information in a whole image, both for tracking and reconstruction. So an important paper for us was DTAM in 2011, where Richard showed that we could build a fully dense SLAM system, which both built a complete kind of surface level reconstruction of a scene, and then used that whole scene also for tracking. So this was a system that didn't use feature points at all. Also, very much at the same kind of time, and also involving Richard, commodity depth cameras came along, and the Connect Fusion algorithm in particular showed what could really be done in terms of real-time SLAM using the pretty high quality flow of depth images that comes from something like a Connect camera. So whereas in the monocular SLAM work of DTAM and so on, we'd had to do quite a lot of difficult stuff in order to get dense depth maps out of a single moving RGB camera. With a Connect camera, they come flying at you at 30 frames per second. They're pretty good quality, and we could really focus on how could you fuse those into a long-term persistent map of a scene. So in Connect Fusion, using a volumetric representation. So just to very quickly show you, something representative of dense SLAM. So this is the elastic fusion algorithm. So this was developed in the Davison robotics lab, led by Tom Whelan, this work a few years ago. And what's happening here is we're jointly estimating the motion of a camera, so a depth camera represented by this little moving purple shape here. And then at the same time, we're building this dense 3D map of the scene. So here we're using a slightly different representation. We're using a circle map, which is a quite efficient way of representing surfaces as a kind of splatting of many disks. A particularly nice point about this representation is it enables loop closure. So when we come round, identify that we've revisited somewhere that we've been before, but there's a bit of drift in the map, we can correct that drift by basically bending the map round quite efficiently. Okay, so that's elastic fusion. And then really, I think what's very much a current area of research interest in SLAM is semantic level mapping. And there's many different approaches to this. One that we developed in 2017 was called semantic fusion. So in fact, I would characterize this as sort of the most obvious thing that you can do. So we're using exactly the same elastic fusion algorithm I just showed you for the dense mapping components of this system. And then we're using a CNN on a per frame basis to label frames with the expected labels in image space. And then what semantic fusion does is fuse all of those labels coherently into the 3D map. So actually each circle of the elastic fusion map holds a distribution over estimated categories of semantic classes, which gradually is refined over time. So you might get a single frame view of the scene, and then you gradually improve the semantic labels by seeing the scene from different viewpoints. Okay, so that in some ways leads me to the sort of crux of my talk. So in many ways, we can look at this progress over the years, this stepping up through the levels, and think of what's happened as we've thrown, more and more computation at the SLAM problem. So, through the years, better computers became available that we could use to run SLAM on in real time, and that's enabled us to do more. But some of the characteristics of that is it's led us to a lot of computation and quite complicated systems. So this is a sketch of a sort of rough idea of the computation graph of semantic fusion, the system I just showed you earlier. And don't worry at all about the details and whether or not you can read these. Roughly speaking, the green blocks are the kind of main data stores here, and the yellow blocks are computation blocks, and then they're joined together in this graph. So we've got all sorts of different things going on. We've got CNNs doing work labeling images. We've got a sort of tracking loop here where we calculate photometric errors and optimize. So I just want to make the point that this pretty complicated graph is really what we need to optimize in order to get to this high performance, efficient spatial AI that I'm talking about. And some of the problems at the moment, aside this kind of complication, one problem is that generally different parts of this might be running on different sorts of computation hardware. So some of these parts are actually very nicely parallelized on a GPU, like the CNN, like parts of the dense tracking loop, but other parts don't really work well on a GPU at all. So we have to shift memory back to a CPU, do some optimization there, shift things back to a GPU, etc. And just another key part is a lot of these blocks of data, they're just enormous. So for instance, the map in Elastic Fusion might consist of 5 million circles. So it's just a huge amount of memory. We're pumping around kind of image-sized arrays and video all over the place. So that's very, very expensive in terms of power usage on computation hardware. So to attack these kind of issues and to get to better efficiency, I think there are two kind of main interesting lines of attack, and both of them we're following in our lab. One is about representation, which I think is mainly about how do we get away from these huge sort of representations towards something that's much more small, abstract, and meaningful. And the other is about computation hardware that I'll talk about second. But let's think about representation first, and we should really discuss the impact here that deep learning has had on SLAM, which has certainly been huge. But as Daniel also mentioned earlier, it's certainly not blown away, all of the stuff that we did before. So unlike I think a lot of areas of computer vision, the classical methods are holding up pretty well in SLAM. So I've got a pretty open mind about this, and actually I like to think that there's pretty much a sliding, almost continuous scale that we can consider here when we're designing algorithms. So at one end, you've got this concept of a pure end-to-end learned algorithm where you literally have the data from your sensors coming in at one end, the kind of performance and the things you want to estimate at the other end that you'll measure it against, and in between some complete black box network that will learn whatever structure it needs in order to best achieve those ends. At the other end of the scale, we've got a fully hand-designed algorithm. So certainly up until quite recently, this is what SLAM algorithms were. So certainly something like Elastic Fusion, purely hand-designed. Semantic Fusion, uses some CNNs. So there are some learned blocks in an algorithm like that. But I think there's many different points on this sliding scale in between those two ideas. And most of us in SLAM are working on quite modular ways of designing systems somewhere in the middle of that sliding scale. And there are probably two key ways to go about that. One is you start with your hand-designed algorithm, this big kind of graph of components, and you replace some of those designed modules with learned modules. I think the other approach is to start with a sort of end-to-end algorithm, but then engineer structure into that algorithm. So maybe you'll replace some general learned block with something like a spatial transformer, which has a much more sort of human design that's gone into its structure. But you may end up in very similar places in those two approaches. So actually, my main interest at the moment is not so much whether these modules are learned or designed. I think we're going to see great progress in both of those, but how they all connect together, what is the computational kind of layout and structure, how do they communicate in each other, what's really going to lead us to this efficient spatial AI capability that I've been talking about. So just to show you some of our work on representation that we've done recently. So one kind of key area we focused on, I would describe broadly as coded keyframe representation. So one very nice way of going about SLAM is to make a map of keyframes where you're estimating the pose of the camera at various places in your environment, and relative to each of those, you're estimating certain quantities, such as a depth map, such as a semantic label map. And we've shown with a couple of papers recently, so CodeSLAM from 2 years ago at CVPR, and then Scene Code from last year, that we can use deep learning. So don't worry too much about the details here, but there's a combination here of something that's like a single view depth or semantics prediction network combined with some variational autoencoders. So the capability that this gives is when you feed an image in, so this is an image from Scene Code, and in Scene Code we're interested in both depth and semantic labels for each of these keyframes in our system. So we get a single view prediction of both a depth map and of a semantic label map, but then we also have available these codes here. So these are part of the autoencoders, which are basically vectors of small numbers of parameters, so typically something like 32 parameters, which are like sliders that then allow you to adjust the depth or semantic map that you've built. So from a single view, you predict a depth map, but then when you've got two views overlapping, you can adjust the codes of these two predictions to try and make them meet each other. But the nice point is that these codes alter the depth or semantic maps in nice, smooth ways that are consistent with things that happen in the data set. So this actually enables us to do jointly optimized dense SLAM, both for depth and semantics, just by optimizing fairly small codes. And if you're interested actually in these methods and playing around with these kind of ideas, I would highly recommend looking at this paper. Let me just quickly show you the video here. So this is work led by Jan Zarnowski from our lab, and it's an evolution and a turning into a much more kind of proper SLAM system of the ideas that are in CodeSLAM to enable, you know, sequential joint optimization of both camera motion and then dense scene geometry via this code optimization method. And we've also just recently released all the source code behind this open source. So please have a play with that. Okay, let's keep moving. So those methods use deep learning to kind of learn representations of kind of whole frames, but actually, you know, you realize some of the limitations there, that actually 32 parameters is really not that much for describing the variation that can happen in a whole kind of depth map or in a whole image scale scene. I think that where we'd really like to go in general in terms of thinking about what the representations of these maps should be much more focused on what are really the important things in scenes for robots or other smart entities. And I think that kind of comes down to objects. So a map of where the objects are in a scene seems to be something that you could encode really quite efficiently and might really be the right way to go about, you know, storing long-term information about scenes. And we did some work back in 2013. This was led by Renato Salas Moreno on a system called SLAM++, which was really the idea of, can we directly build a SLAM map at the units of objects? So this was bringing object recognition directly into the front end of a SLAM system. So as we were moving a depth camera around, we would recognize instances of known 3D objects, so these tables and chairs, and then when we'd recognized one, we would populate the map with an object like that. So the map really just existed of a graph of the locations of objects. So each of these objects, we just need one 3D model for each of these types of objects. And then we just need to store the 3D coordinates of those objects. And we can bring all of those things together into a pose graph. So very efficient, but with the limitation that the map can only consist of these specific sorts of objects that we know about in advance. But I think this work has been quite influential and you know, really leading a lot of people to think about this concept of, you know, what's the best way to represent scenes in terms of graphs of meaningful entities. So SLAM++ is about a kind of one-level graph of objects, but you can really extend that in a sort of hierarchical concept. So here's a couple of images from different projects from Facebook Reality Labs or from Luca Carlone's group at MIT. How do you decompose scenes, in a hierarchical way into these sort of hierarchies of objects, which are actually very different, very similar to the sort of scene graphs that, for instance, a computer game designer would be familiar with for designing 3D scenes. So just going back to the SLAM++ concept, let me show you some very recent work. So in fact, we'll be presenting this this week at CVPR. Oh, let me just make sure that's muted. So this is called More Fusion. So this is a system which is very much along the same lines of SLAM++. If we want to build a map of a set of objects for which we have prior CAD models available. And here we're using these YCB objects. And you'll see that we've moved it over to, rather than a kind of room scale setting, this is a kind of tabletop setting, but where we've got now a robot arm involved. So the reason to build this representation of where the objects are in the scene is because we actually want to go in and interact with them. So the kind of extra tricky point about this setup, rather than what we had in SLAM++, is now the objects tend to be very close together, they're lying on top of each other, they're occluding each other. So it's actually quite tough to get an accurate estimate of the relative poses of all of those objects. So here we use multi-object volumetric reasoning to say that we want to estimate a set of 3D estimates of all of those objects, but clearly under the condition that they can't be intersecting each other. So that means that's what gives us the extra information that allows us to, estimate good pose even for objects that are, tricky, that they're occluded. We can only see a small part of them. So we get to these very nice kind of 3D representations of scenes, and then I can show you here how we can now use that for grasping. So in this particular demo, so we were showing it in a kind of 3D visualization on the left, and in the real robot video on the right, the robot wants to grasp the red box and move it into the brown box at the side, but it realizes that there are two objects kind of in the way. So having mapped the location of all the objects in the scene, it can then go and grasp these distractor objects, move them out the way, put them into the yellow bin on the left, and then finally go in and grasp this red box and put it in the correct place. And you'll notice that it's not just dropping it into this box, it's actually placing it quite precisely because it's picked it up with very good, perfect knowledge of its pose. So that work relates to some other things that we've done, still very much in this area of object representation. So we had a paper a couple of years ago called Fusion++, which is saying if we're not in this strong situation of knowledge of having prior CAD models for all the objects we expect to encounter, what can we do? Well, we can use something like mask RCNN to at least identify what the separable objects are in the scene. But for each one, we'll build an individual volumetric reconstruction, and then our total high-level representation is a graph then of these individually reconstructed objects. Something that we've published very recently is a system called MonoSLAM, which I think lies very much in between Fusion++ and SLAM++. So SLAM++, you've got prior CAD models. Fusion++, you have no prior knowledge of objects. In between, I think you have this interesting area where you can recognize an object at the level of its category, but not necessarily in terms of its precise instance shape. So we've got here learned class level shape descriptors. So here we've got 4 classes of objects, bottles, mugs, bowls, and cans here. For each one of those, we've taken a 3D database of objects of that class. We've learned with a 3D autoencoder a shape space for each one of those objects. And then at runtime, we're optimizing a code relative to each one of those shape spaces to then fit the precise model of the objects to the runtime data that we've got. So let me just skip forward a bit. So here's a visualization now of a sort of object level SLAM system using these descriptors. So here it's detecting the objects Each one, it's then optimizing these shape parameters, and then it's putting all of that into a full joint optimization of camera pose, of object positions, and of object codes. And then I'd show you here, we've also used this system for robot grasping. So here's a situation where the robot's looking at this scene. It's got a number of objects in it. It doesn't have precise CAD models for any of these objects, but it fits these shape descriptors. And then we show that they're fitted accurately enough that then we can then go and grasp the objects very precisely. So what it's doing here is grasping these bowl objects in order of size. So the biggest one first, and the smallest one last, and then it's placing them precisely like this to stack them in the corner of the box. So this, I hope, really sort of shows how we're really now trying to go beyond SLAM, where the endpoint goal is just representation and map, but the endpoint goal is actually intelligent action. Okay, so we've just got a few minutes left. But let's just go back to this picture I showed you earlier of the semantic fusion computation graph, and talk about the other kind of key approach that I think is very important at the moment, and that's related to hardware. So I mentioned that different parts of this computation graph in the current system are running on different sorts of processors. So mostly some on CPU, some on GPU, and we've really directly experienced the impact that new processing hardware coming into the field has had. So when GPUs became available, we were really able to do new things in SLAM. But we've got to realize that's only the start or an ongoing part of the evolution of computer hardware. So this is something I've been very interested in, particularly since being involved in a project called Pamela, which was a joint project between the universities of Manchester, Edinburgh, and Imperial a few years ago, where we really thought about how do SLAM algorithms relate to the hardware that they're going to run on. And we took some SLAM algorithms and really broke them down into their components, and really analyzed how the different parts of those components worked, you know, on anything from a huge desktop GPU-enabled system down to a tiny embedded board. And remember that, you know, the target for the sort of systems we really want to run these algorithms on is much more like this than this, or at least the future version of a low power system like this. So we were trying to kind of open up research on different types of algorithms, and maybe how algorithms should be co-designed with hardware. And something that we were always thinking about at the time was, could we or should we design a specific chip for SLAM, which would be the most efficient chip possible? And I think the hard thing about that for me was, people would ask me, okay, what's the algorithm we should implement, and then we'll go away and design some hardware. But I didn't want to be pinned down, because the algorithm space was changing so fast. We had sparse, dense semantic CNNs coming in, and I didn't want to be limited too much. So what is the right sort of hardware for SLAM? And I think that's still an open question, but there've been very interesting things going on recently, which I think are promising. And in particular, a move to a new sort of processing hardware called a graph processor. So this is particularly a visualization from a company in the UK called GraphCore that are actually building graph processors. And they call it an IPU, or an intelligence processing unit, to mean that this is really a processor designed for AI workloads. And I would certainly include vision within AI. So, let's remember that we've done all this work on computer vision and AI using processors that weren't really designed for it. So we've used CPUs an awful lot. They're general purpose processors. They're good at word processing or something like that, but they're not necessarily got the right sort of performance for AI. We've used GPUs a lot. They're designed for graphics primarily. They've been adapted a lot to AI, and for certain workloads in AI, they're very useful, but they certainly don't solve the whole problem. So an IPU is, again, not trying to be really specific, but it has certain characteristics that I think make it much more suitable for what we want. So what an IPU actually has, it's a massively parallel processor, a bit like a GPU in that sense, but all of its different processing cores can be running quite different sorts of programs. So whereas a GPU works best when every core is doing very much the same thing in lockstep parallel, an IPU can be much more flexible. And part of the design of an IPU, and this isn't at all how it's laid out, but just to show you the sort of split between logic and memory on an IPU, compared to a GPU, there's much more of the area of the chip is given over to memory. So think of a larger number of processors set into this sea of high performance memory, such that each of the cores has quite a lot of memory to be able to work with, but it can also use that memory to very efficiently store and communicate things to its neighbors. So actually the general class of algorithms that an IPU is really good at is local processing and storage algorithms which compute by message passing. So many independent cores, each computing its own thing, and then sending lots of messages around to all of their neighbors. So if you can make algorithms that work like that, they'll work very well on an IPU. So I've been thinking a lot about spatial AI, and in particular, where are the graphs in spatial AI, and how might we map those graphs onto something like an IPU. So this is a visualization that GraphCore have produced. So when they take a neural network and compile it down to run on an IPU, and that's the main thing they're commercially working on at the moment, they can produce this nice visualization of which parts of the neural network map really sort of geographically to the different parts of the processing and storage array. I've been thinking about spatial AI and what are the graphs in spatial AI, and how might we map them therefore to processing hardware. And parts of this look very much like that yellow graph that I showed you earlier. We've got these graphs of computations and how they link together. But there's a lot of other graphs in SLAM that will be familiar to researchers in SLAM. So for instance, most of the best ways of storing maps in SLAM come down to graph-like representations, which essentially connect nearby places together closely in the graph and faraway places not so much. There's also some very nice kind of graphs you can find, related to camera space. You've got this regular, graph of coordinates in an image, which we use for MRFs and things like that. So a lot of the thinking in this paper is related to that kind of thing. So making that a little bit more concrete, and this is the last slide I'm going to show, but we've got a paper that we're going to present at CVPR this year, so led by Joe Ortiz. It's called Bundle Adjustment on a Graph Processor. So this relates to another one of these very long discussion papers, which is the second in my future mapping series, called Gaussian Belief Propagation for Spatial AI. So having thought about this a lot, I've realized that there are categories of algorithms which we can use in SLAM and spatial AI, which might be very suitable for this sort of new architecture. And interestingly, these are not new algorithms, these are old algorithms. So belief propagation is a well-known classical algorithm. It's been used various times in computer vision, but not really in SLAM type of problems. Because if you want to do something like bundle adjustment, where you want to jointly estimate the positions of a set of points and a set of cameras, there are algorithms that work more efficiently on a CPU than Gaussian belief propagation. But on an IPU, we've shown that you can actually implement Gaussian belief propagation very efficiently. So this paper shows that, so we take a kind of reasonable size bundle adjustment problem, we map it in quite a simple way down onto the IPU. So we take the points, the cameras, and the measurement factors in a factor graph, map that down geographically onto a graph processor, and then implement bundle adjustment by belief propagation. And really, in very preliminary results, we're already showing very promising things, like a certain size of bundle adjustment problem can be computed 20 or 40 times faster on an IPU than it can be on a sort of equivalent size CPU using commercial software like Ceres. So for me, this is very interesting and promising, and it takes me towards larger scale thinking about how we might move towards fully graph-based representations for spatial AI. And the dream is to have this graph living and evolving on something like an IPU. Data gets fed to it, and all the computation is kind of local and in place on an IPU. We've got very general factor graph formulation that allows us to think of all sorts of different measurements, sensors, and priors, all contributing to the same graph, and gradually leading us towards this more abstract and useful representation. So have a look at this paper if you're more interested in the details of that. Okay, I've finish there. So let me just quickly make some conclusions. So I think spatial AI research is very exciting. So some of the key things to work on are efficient 3D scene representations and systems for incremental scene understanding, co-design of processes, sensors, and algorithms, and graph-based algorithms for estimation, such as belief propagation. I'm also very interested in graph-based algorithms for machine learning, but I don't yet have much experience in that area. And just quickly to mention and to thank my colleagues at my affiliations. So the Dyson Robotics Lab that I lead at Imperial College, it's an academic lab funded by Dyson, collaborating with Dyson, where we do academic long-term research on SLAM, scene understanding and manipulation. And I'm also co-founder of the London-based startup called SLAMcore, which develops applied spatial AI solutions. So thank you very much.
Thank you very much, Andrew. I'm sure we can imagine over 300 people applauding right now, including me. So thanks again. We have some questions posted. So let me just pick some. There is there is one that is I find also interesting. Is what are the differences for a spatial AI from the point of view of applications like AR indoor or self-driving scenarios outdoor?
What are the differences? So yeah, as I mentioned, so I would hope that there's a lot of commonality between the spatial AI system that might apply to either of those situations, but with certain both constraints and parameters of performance that would differ. So clearly, indoors versus outdoors, there's going to be different categories of objects and that you would need to semantically represent. There's going to be different levels of accuracy needed, maybe different levels of speed of your platform, and different sorts of sensors available. So outdoors, for instance, you've in a driving scenario, you'll probably have some prior maps to rely on. We know the map of a scene. We'll also have strong knowledge, for instance, that cars are moving essentially on the 2D plane of the road and moving in this non-holonomic way that cars drive. On the other hand, there are things that make it very challenging, like extreme safety constraints. Make a bad mistake and it's very serious. Indoors, there are other things that make it more challenging. There's a lot more variety of objects indoors. There's often rooms with huge blank white walls that are very hard to deal with. Maybe there are people and maybe animals or other things moving in close proximity. So I think that there's definitely going to be different challenges, but I hope that there are core elements of just how you would design the essential, graph-like structure of how to represent that scene to enable useful action, which I think would be common.
Okay, so I have another one in the whole system. As you presented, there are so many components and connect together. So is there one in particular that is holding the rest sort of back in terms of what's required in general?
Yeah, that's a really good question. Yeah, I'm not sure I could really put my finger exactly on one. So I think in terms of a performance parameter where it feels like we're not there yet, it's sort of robustness and the ability to deal with changing situations. So that really involves a lot of the components of the system. But for instance, in semantic labeling and scene understanding, we've probably all had these experiences where you train your system on some particular data set and then you try it. You wave a camera around in the room that you're in, and it really doesn't work that well. So how do we overcome that? I think some of the things I'm most interested in at the moment involve more sort of unsupervised learning type of methods, and this idea perhaps of scene-specific networks. So you might actually expect, you buy a cleaning robot and put it into your home. I think it's reasonable to expect that robot will actually do some quite scene-specific learning within that space and then maybe even ask you a few questions. It needs a few labels probably, but hopefully not too many. But yeah, to what extent can that learning be done in a way that's actually useful to a user? Clearly, what's not going to be available is full, labeled data of every scene that it's going to go into. So what combination of, transferring things from other scenes, using, unsupervised learning just to make use of unlabeled data that it can get for itself, and then I think a small amount of labeling that it could get maybe by, asking questions of its owner or user would enable the right performance.
Okay, so there are also a couple of questions actually related to scene code, and let me combine them. So what do you think is sort of particularly well suited for SLAM in terms of codes in VAE, and what is the trade-off between representation and FE that you have to strike somehow?
Yeah, so I think speaking specifically about scene code and code SLAM, those kind of methods. So they're really trying to give you a sort of optimizable basis for depth and semantic labels. So we know that single view prediction is quite good. So single view depth or single view labels, but we find that often there might tend to be some quite gross errors. So for instance, if I point a camera at a wall, it will probably do a quite good job of telling me this is a flat region, but it may be that it's a meter or two off with the absolute depth of that wall or with the orientation of that wall, for instance. And the same with semantic labels. So if I point it at a flat region in my scene, it may not be sure whether that's part of a floor or part of a table. Those two things are just quite ambiguous. So we want to give the ability to do multi-view optimization, but in a smart way. So compared to semantic fusion, if you want to take single view labels from multiple views and fuse them, you do that just by per pixel averaging the labels. And what that tends to give you is this very sort of noisy type of fusion. So whereas what we do in scene code is we do code fusion by joint code optimization. So if there's one image where a certain region is labeled as a table and one image where it's labeled as a floor, it's not just going to kind of average those things. It's going to find really which of those two is most consistent with everything else. And then, what should happen and what normally happens is the whole of that region will eventually confidently turn to one or other of those classes, which is the most sensible thing to do.
Okay, maybe a final question. In the context of IPU chip, how to deal with a long-term SLAM problem? If there are limits on the chip in terms of memory, of course.
Yeah, no, that's in fact very very much something we're thinking about at the moment. So this idea in a on a chip like that, I think what you really want to do is sort of take your factor graph, which is representing your whole estimation problem, and sort of lay it out geographically on that chip, and then do in place computation. But clearly, it's a problem if your graph just gets bigger and bigger. It's eventually not going to fit onto the chip at all. The chip has limited memory. I think the right route there, and what we're very much working on, is incremental abstraction. So imagine that you'd detected and mapped 100, let's think of just points at the moment, on something like a wall. At some point in time later, you're going to hopefully realize that there's a simpler structure that describes that 100 points. And it could be that there's an external, maybe a neural network has looked at that frame and given you a fairly confident prediction that, you know, this region of the image looks planar. Or maybe just by, you know, pure introspection, those 100 nodes, by talking to each other, have realized, hey, guys, you know, it seems like we're all quite coplanar here. So I would then think the right thing to do is to replace those 100 nodes by a single sort of supernode with the parameters of a plane, which then connects to all the other things that the individual points were connected to, and you've turned 100 points into 1 point. And if you can then do that in, you know, incrementally and eventually hierarchically, so maybe, you know, you simplify to planar regions, and then different planar regions join themselves up into large planes, and then maybe multiple orthogonal planes join themselves up into boxes and rooms and things like that. That for me seems like a way that you can just keep going. You can keep your graph of a sort of bounded size and keep this purely graph-like operation.
Excellent. Thank you very much again. And let me thank both speakers for a great talk. And yeah, I just give a quick applause from everyone in YouTube and Zoom. And so that is the first part of 2 invited talks of this morning. So thank you, Andrew.
Thank you.
And let me hand over to Wang that will now present the challenge.